Yeah. Okay. Okay. Bismillah ar-Rahman ar-Rahim. So how do you maximize the screen? How do you? It is already maximized. Okay. So today we will do generators. Okay. First of all, what are generators? You know, I always ask the meaning of the title. Whenever we start a new chapter, I always ask the meaning of the title. So what do you understand by generators? What do they do? Yes.
They convert mechanical energy into electrical energy.
Very good. Yes. Yes. Thank you. Also, another question, what do you understand by this electromagnetic induction? What is induction? You must have come across this term before as well. Remember, in charges are induced, induction of charges, right? So do you understand the meaning of induction?
Yes.
Yes, Hala? Yes?
It is the transferring of any magnetic field or energy without touching the surface.
Very good. It is the transfer of, can you repeat? It is the transfer of, so can you please lower the camera?
So I said field, any magnetic field or energy.
Yeah, it is a transfer of magnetism. It is the transfer of magnetism or electricity from one object to another without them actually touching each other. Okay, without touching, if one object can transfer its charge or its magnetism onto the other object, that is called induction. Okay, so once you understand the meaning of the term induction, then it's easier for you to understand. So this is electromagnetic induction. So both magnetism and electricity. What do we mean by electricity? Charge. That's what we mean, charge or current. That is induced, or that is given, or that is created, whatever word you want to use, in the other object without touching it. Okay, so now is the camera okay? Yeah, this is good. Yes. Okay, so that's what's happening here, electromagnetic induction. Okay. Okay, now, so there's this wire. It's a conductor because it's made up of metal. It does not have any current. Now we will induce a current in it. How? By making it pass through a magnetic field. Now they are using this U-shaped magnet. One arm is North Pole and the other arm is South Pole. Okay. And so there is magnetic field between the two poles. And when we are moving this conductor, it is cutting those lines, right? Remember, when a conductor cuts a magnetic field perpendicularly, when I'm repeating myself, when a conductor cuts a magnetic field, when I'm using the word cut, meaning that it should not be parallel. The conductor should not be parallel to the magnetic field. By the way, there are simulations, PHET simulations. I will share the link in the group. Go ahead and watch those simulations. You will understand what I mean. So this conductor should be actually cutting the magnetic field lines. Okay. So the maximum cutting will be when it is cutting perpendicularly, right? This, for example, this arrow, think of this arrow as the magnetic field lines. Okay, what is the direction of magnetic field lines? Does anybody know? How do you find out the direction of magnetic field line? Yes, Hala? Yes, Hala?
It's from north to south.
Yes, it is from north to south. So remember, whenever you are asked to draw the direction of a magnetic field, it should, you will assume a north pole. How will a north pole behave? How will a north pole, where will the north pole be directed? that will be the direction of the magnetic field. So here the North Pole would be repelled by this pole and will be facing the South Pole, right? So let me make this diagram here. So this is the magnetic field. This is the magnetic field. So if this is north, this is south, the direction would be this way from north to south. And if the conductor, so how can the conductor cut it? Conductor can cut it perpendicularly, right at 90 degrees, or less than 90, or even less. And the angle will keep decreasing as you are moving from perpendicular to horizontal until it gets parallel, till it gets parallel to the magnetic field line. And then it can increase in the reverse direction. The conductor can start moving in the reverse direction, and then again it becomes perpendicular, and so on and so forth. So what I'm saying is that when the conductor cuts a line, and by cutting I mean any of these angles other than the parallel, I'm not talking about the parallel, but other than parallel, when the conductor cuts the magnetic field lines starting from 90 all the way, a current is induced. A current is induced, and basically a voltage is induced within the conductor, okay, within this metal wire. So there will be a potential difference or a voltage produced between these two ends of the wire, which will make the electrons in the metal flow from one end to the other, right? From positive to negative. So this is called induction. So why this is called electromagnetic induction. Now, just one thing that I want to mention is that when the conductor is conducting the magnetic field perpendicularly, at that perpendicular cut, the current or the voltage is the maximum. Okay, not the current, I'm sorry. The voltage is maximum. Okay, remember, voltage is maximum. And as the angle is decreasing with the magnetic field, the voltage is also decreasing. Okay, so much so that when the conductor gets parallel to the magnetic field line, the voltage is 0, right? And then again, the voltage increases, but this time in the opposite direction. And then it becomes maximum here in the maximum negative value. And then again, it starts decreasing till it becomes 0. And then again, it increases till it becomes 90. I mean, till it becomes maximum. So this is called electromagnetic induction. So we used a magnet and we induced a current in the wire without connecting it to any battery. We did not use any battery. This is like a galvanometer. It is detecting the current. It is detecting the current. It's not supplying the current. Okay, so this wire is a simple wire and it's not connected with any battery. But just because it is cutting the magnetic field lines of this magnet, therefore a potential difference or a voltage is produced between the two ends, and therefore the current is flowing. Okay, this is electromagnetic, and this galvanometer is detecting the current. Also, when it is moving up, the needle will move to one side, and when you will move it down, the needle will move to the other side. Okay, so as you are moving, as the direction of the movement, as the direction of the movement of conductor changes, the direction of the current also changes. Okay, so if, for example, the conductor moves up, the current has a particular direction, for example, this way. When it will move down, when the wire is moved down, the current direction would reverse. Okay, okay. So after you have understood this, then okay, now they are checking out that is this true? So we were moving the conductor in the magnetic field, right? But what if we move the magnet in an electric field? Will we get the same thing? So this time they have coil, they have a metallic wire, and they have They have coiled it. Okay, it's like it's called a solenoid. Okay, it's like a cylinder wire like this. Okay, so it's a wire which is coiled around to give you a solenoid. Okay, so it's a 3D cylindrical shape, but it's a wire which is wrapped around. So if we have a wire and we have current, okay, so no, this is not attached to the battery. Okay, so we have a wire, okay, and now the magnet is being moved in. Now, is there any potential difference being created? The answer is yes. Yes, again. So that means that the conductor has to cut the magnetic field lines. Either the conductor can move or the magnetic field lines can move. Either way, potential difference will be created. Okay, so again, the current is induced in the coil by the movement of magnet going in and coming out, going in and being drawn out, right? So you understood this, right? Okay, okay. Then Faraday's law. So Faraday carried out these investigations, and then he came to this conclusion. By these two experiments, he came to this conclusion, that the induced potential difference, whatever potential difference is induced, is dependent upon the speed of motion of the magnet, like how quickly are the magnetic field lines being cut by the conductor, how quickly, and how many lines are being cut, and how strong is the magnetic field. How strong is the magnetic field? Okay. What is the difference between a strong and a weak magnetic field? By looking at the magnetic field diagram, how can you say that a magnetic field is strong or weak? Any idea? Huh? Any idea? If, for example, I make this.
When the north and south poles are closer together, the field is stronger.
North and south pole? Okay, now tell me this.
When the magnetic field lines are closer, they are stronger.
Yes, good job, Myra. Yeah, so this is stronger when the field lines are closer together in the same area. So if the area is the same, but there are more lines here, that means this is a stronger magnet. I'm sorry, I drew two of them by mistake, one magnet, okay? And please don't mind my drawing. Okay, so okay, so you got, so if we use a stronger magnet, there are more magnetic field lines, so more lines being cut. So you can either increase the number of the coils of the wire, either you can increase the number of coils of the wire, or you can use a stronger magnet, or both. Okay, so when you'll do that, what will happen? You will produce a greater potential difference. When you will increase the number of coils, or you will use a stronger magnet, you will have a greater potential difference. Okay, or if you increase the speed of it going in and out, if you do it real fast, then that will also increase the potential difference. So these three things: speed of motion of the magnet, number of turns on the coil, or strength of the magnet. So remember this, that the more the lines are cut, the faster the lines are cut. And also it has to do with the angle. Remember the angle. So if the conductor is, so the maximum potential difference is when the conductor is cutting the lines perpendicularly, and the least zero is parallel. Okay, and then we have in between. Okay, so the size of the induced potential difference is directly proportional to the rate at which the conductor cuts the magnetic field lines. Also in previous chapters, from the previous chapters, you must know that when, so now the magnetic field is inducing current, right? Now, is it possible that you have current flowing through a straight wire and magnetic field lines are created around it? Does that happen?
Yes.
Yes?
Yes.
Yes. Yes. So here the magnetic field lines are producing electricity, right? Here the cutting of magnetic field line is producing electricity. But then in this chapter, I'll show you, just keep that in mind because you will need it. Okay, I cannot find it, leave it. So, but remember that if you have a single wire this way, and there is current passing through it, there will be magnetic field created around it. Okay, like this. I think you have done it, right? Yeah. So remember that as well. Now, this Lenz's law, what does he say? Now, he is coming up with a, okay, no, the direction of the induced current is such as to oppose the change causing it. Yes. So remember, in nature, in science, things try to balance the change that is causing it, right? It's usually like that. Yeah, also Lenz's law is an example of the principle of conservation of energy. Now, what is the principle of conservation of energy? Does anybody remember? What is the principle of conservation of energy? I think it's very simple. Yes, Hala?
The energy cannot be created or destroyed. It can only be left out as heat.
The first part is correct, but only the last part. Yes, energy can neither be created nor destroyed, but it only changes from one form to another. It only changes its forms, right? It cannot be created or destroyed. I mean, it cannot be created out of nothing, and it will not vanish either, but it will only change its forms. So this is one example, and we will see how. So now what Lenz's law is saying is that if this is a coil and there is, yeah, okay, if this is an coil made up of a metallic wire, and we introduce or we bring a magnet close to it, this will automatically behave as a magnet itself. Why? Because a current is induced in it. And remember, when a wire has electricity passing through it, it has magnetic field around it. Remember? I just told you. So when a wire has a current passing through it, it behaves as a magnet. I mean, it has magnetic field around it. So when this magnet is brought close to it, it tries to oppose this coming in of the magnet by repelling it. How? By turning into a magnet in such a way that this end becomes the north pole of it and this becomes the south pole. Okay, this becomes the north pole and this becomes the south pole. So north and north will repel. So it's like, don't come inside me, you know, like that. So it's opposing the change which is causing it. And this current is induced by what? By this magnet coming closer to it. So when it is coming closer to it, what's happening? There are magnetic field lines, right? Like this. The magnetic field lines. As this magnet is, so as this magnet is coming closer, what's happening? These magnetic field lines are coming closer. And as they're coming closer, what's happening? Can you see the wire is cutting them? The wire is cutting them. And so that is inducing current in this wire. That is inducing current in the wire, and that current can be detected with the help of this galvanometer. And that is also turning this coil into a magnet in such a way that it is repelling this. Now, the opposite is happening here. Here, the magnet is being pulled out. So again, when it is moving, the magnetic fields are also moving away with the magnet. And in doing so, again, the wires are cutting the magnetic fields. There is relative motion. So remember, whenever there is relative motion between the magnetic field lines and the conductor, you will have a voltage induced in a metallic wire. Okay, and if it is in the form of a solenoid, if it is in the form of a coiled, if it is in the coiled form, then it will behave as a magnet, and in such a way that it will try to oppose. So this will now try to attract. So this will turn into a south pole attracting the north pole, saying don't go, like that. Okay, so in both the cases, the coil is opposing. The current is induced in such a way. The current is induced in such a way. What do we mean by that, that the current is induced in such a way? Meaning the direction of the current. The direction of the current in such a way so as to oppose the change which is causing it. Okay. Now, what they are saying here is that Lenz's law is an example of the principle of conservation of energy, because if, for example, let's suppose this turned into a magnet which would further attract it, then this magnet would enter it really quick, turning this energy into kinetic energy as well. Now, where did that energy come from? So that would mean that energy, that electrical energy, is created from nothing. So that is why this opposition is showing, is just verifying the principle of conservation of energy, that this energy of bringing the magnet in, this is like kinetic energy, right? You are moving the magnetic bar inside. That kinetic energy is converted into electrical energy, right? Okay, now Lenz's, okay, for a straight wire moving at right angles to a magnetic field, a more useful form of Lenz's law is Fleming's right-hand rule. Okay, so this is Fleming's right-hand rule. Now, there are a lot of rules here in electromagnetism. I think there was this Maxwell's rule, screw. Yeah, and then there is this left-hand rule, right-hand rule. So just remember when to use which rule. I think there are 3 to 4, if I'm not mistaken, but yeah, just try to remember when to use which rule, okay? So, okay, Fleming's right-hand rule is used for electromagnetic induction. Okay, it is used for electromagnetic induction, meaning when the current is induced by the magnet. Okay, so this is the hand. Okay, it's the first finger. So remember, with these letters, first finger will show you the direction of the magnetic field, F4 field, F4. First finger, second finger, K, the C is for the current, the direction of current in the wire, and thumbs, M is for motion. Okay, also appreciate that all 3 are perpendicular to each other in 3 dimensions. They are perpendicular to each other in 3 dimensions. Okay, now we will use this phenomenon to understand this simple AC generator. So generator, as you just said, converts mechanical energy, in this case, kinetic energy, into electrical energy. And this energy, this electricity is going to be AC. AC means what? What does it mean, AC? Sundar, loudly.
It means alternating current.
Yes, it means alternating current. Yes, alternating current means, loudly, beta, for the class, please.
It means that it's constantly changing the direction in which it's flowing.
Yes, yes, it is constantly changing its direction. So alternating symbol is this. The symbol for alternating current would be this. This is the symbol they use for alternating current. Okay, it means that current is going in this direction and then back, and then this, then again forward, then backward, forward, backward, forward, backward. You know, just like you have swing going back and forth, back and forth. So the same way, forward, backward, like that. That's called AC. DC, you have only one way from, convention is from positive to negative. Conventional current is from positive to negative, and the actual flow is from negative to positive. Remember that? So we usually use convention for our circuit diagrams. So how does this generator create that alternating current? So it is converting kinetic energy into electrical and alternating current. Electrical energy in the form of alternating current. Now let's see. Again, they're using two poles of the magnet. So there are magnetic field lines, which they have not drawn. But of course, there are magnetic field lines going from north to south. Okay, now this coil is in the form of a rectangle. It is shaped into a rectangle. Okay, and it is connected to another circuit. There might be another circuit which needs this current. Okay, the circuit can be for any purpose, maybe lighting a lamp, let's say, or anything, and it needs current, and this generator is providing it, that current. Okay, let's suppose that there is a current here, and for example, there's a lamp that we want to light up with the help of this generator. Okay, now we will look at these two arms of this rectangular coil. Okay, we will look at these two arms. Why not this? Why not these two arms? Can anybody answer? Why are we not looking at these two arms? Yes, Hala?
They are parallel to the magnetic field.
Yes, they are always parallel to the magnetic field. Okay, do you understand this? Does everybody understand this? You have to try thinking in the 3D. Think in 3D, okay? In science, you have to imagine a lot. You have to create, you have to imagine, okay? Now, the magnetic field is from from this North Pole to South Pole. So they are like this. So magnetic field is this, okay? And then these arms right now at this position that they have shown in the diagram, at this position, it's already parallel. So it's easy to understand that at this position, it is parallel. But what about when it you know, takes a turn? When it takes a quarter turn, it will be vertical, right? Then what? At the vertical position, what about the vertical position? A vertical position also, it will move parallel, you know, because I wish I had something to show you. Are you understanding what I'm saying? I have to show this 3D. I searched for the simulation for this, but I couldn't find, and I didn't have time to find. Can I have that book? Okay, let me, yes. I like this book better. By the way, when I was a student, when I was in O levels, I used this book. This book taught me physics. And then I searched for it again, and alhamdulillah, I found it again. So I still like to study from this book. Okay, now these two arms we will discuss later, but I'm trying to explain you these two arms. Why are we ignoring these two arms? Is because here you understand that it's parallel, right? Here you understand it's parallel. This arm is parallel to the magnetic field. But even here, when it is vertical, can you see? Yes, okay, another thing, if the metallic conductor is placed inside the magnetic field and it's not moving, it's stationary, and neither are the magnetic field lines are moving, then there will be no voltage. Remember, it's not the presence of a conductor inside a magnetic field which is producing voltage. It is their relative motion. Only if they are moving and cutting, only then voltage will be produced. So though these two arms are there, they look perpendicular, but if you look at their motion, the motion is this. Motion is this. This arrow is showing the direction of motion of this arm. This arm, can you see it is parallel? It's this way, right? And the magnetic field lines are also this way, going this way, and this is also going this way. So they are parallel. Here, this arm is moving, again parallel. Yes, opposite direction, but parallel, still parallel. Angle is very important. So it is only these two arms. It is only these two arms which are cutting the magnetic field line at this position only. Because when it is rectangular, even these two arms are parallel. These two arms are also moving parallel at this vertical position. At this vertical position, all the arms are parallel. All the four arms are parallel at this vertical position. Only at this horizontal position, these two arms are cutting the magnetic field lines perpendicularly, like exactly. Let me show you this graph. So when the coil is vertical, all the arms are parallel. All the arms are parallel to the magnetic field lines, therefore zero current, zero voltage. Zero voltage, zero current. It is only at the horizontal position that these two arms are cutting the magnetic field lines perpendicularly, and therefore you get the maximum voltage and therefore the maximum current. And as you can see here, the angle was decreasing with the magnetic field lines. No, sorry, the angle is, increasing. Yes, the angle is increasing with the magnetic field lines, and therefore the current is also increasing till it reaches maximum. Here again, the angle is decreasing, and therefore the current decreases as the angle is decreasing. Here again, it gets zero. Again, it gets zero. But now it's the other turn. This was half. This was half turn. This is the second half turn. Second half turn. So, किस तरह से हुआ ये? Okay. So again, now the direction is in the reversed. Now the direction has reversed. Okay, of the current and the voltage. Why? Because if you look at this diagram, they have shown you here. Okay, again, they are showing you the same coil, and they have drawn these field lines, and they are showing this coil. Okay, so this is a vertical position. All arms are parallel, moving parallel. All arms are moving parallel, therefore zero, and so on and so forth. And here, this arm, DC and AB arm are cutting perpendicularly, and so maximum voltage. Okay, and again zero, here zero, and now again this is negative. Why? Because now at the point D is arm A, at the place where D was initially is now A, and A's place is taken by D. So the direction of the current is now reversed, and then again zero. Okay, yes, Hala?
Miss, when the coil is vertical, isn't it cutting the field lines at that time?
Yeah, that's what I was trying to explain you, that in the vertical position, none of the arms are cutting the field lines. In the vertical position, all the arms are moving parallel. Look at this. All the arms are moving in this direction, in these two directions. Okay. Try to imagine this in 3D form, and don't be confused by the vertical position of the metallic conductor. Forget the position. See where are they moving. It is the movement which is important. The movement is parallel. The arm looks vertical. It is vertical, but its movement is not vertical. The movement is parallel. I told you it is the movement which is important, the relative movement. What do I mean by relative movement? That it can be either the conductor moving or the magnetic field lines moving, any one of them. Any one of them can be moving. Relative motion meaning relative to each other. One of the two has to move relative to the other, right? If, for example, a bar is moving and the coil is also moving together, then there is no motion. When you are sitting in the car, you are stationary, are you? You are stationary in terms of the car, but you are actually moving with the car, right? Am I confusing you? But I hope you understand relative motion. So just remember that the coil's movement, all the arms movement is parallel to the magnetic field lines. Did you understand? Did you understand?
Yes, miss.
Did you really understand? If you did not, please
Yes, miss.
feel free. Okay. Okay. Now, once we have understood this part, now let's talk about these. The brushes and slip rings. Okay. This book was my teacher. I don't know, still I don't understand but from any other book. There's a new edition of this Stephen Popple, but I don't like the new edition. It's the old one. It's my time. It's exactly the same book. So look at this. If we did not have those slips and brushes, I'm trying to explain you the significance of brushes and slip rings. If we did not have any slip rings or brushes, this is what would happen when it is moving. When this coil or this rectangular coil is moving, you would have twists here. The wires would get twists, right? They would get twisted, and so you won't have a generator which keeps spinning. That won't be possible. So what they did was they came up with this slip rings and brushes. You might want to watch a video, YouTube video on how these generators actually operate or work, and then you will understand it better. I think you should go ahead and watch a video. I didn't get time to pull out a video for you. I wish I could. So what happens is that it does not allow the wire to get twisted. How? It detaches it gets detached and then attaches to the other ring. You know, when one complete rotation is completed, when one rotation is completed, or when one turn is completed, the wires, these brushes, they help in switching the attachment. Maybe you are not understanding when I am explaining you, but if you watch a video, you will understand what I mean. Okay, so that prevents this coil, these wires to get twisted. So they just keep switching their contacts. Okay, and these brushes, they are there to prevent. They are okay, wait. They are made of conductors. Okay, they are made of either graphite or sometimes copper, and to make sure that the current is conducted efficiently enough to this circuit. Now, this circuit will not be moving. This circuit will not be moving. Only this will be moving inside the generator. Okay, so that was that. Okay. So let me, which diagram should I use? Okay. So this is one whole complete turn. This is one whole complete turn of this coil, of this arm. Okay, this is one complete turn, one cycle. Okay, so we have frequency. Frequency is the number of cycles per second per unit time. So how many cycles do you have in 1 second will define the frequency of this generator. Yes, Hala? Yes, Hala?
Miss, the generator is working on an AC supply. So does the coil keep reversing its motion?
No, no. What did you say? The generator is supplying AC current, right? The generator is supplying the AC current, okay? Did you say that? Or did you say that AC
Yes,
current
miss.
is, yes. So generator is supplying AC current. How? In one half of the turn, the direction of current is this, positive. Okay. In the second half of the turn, the voltage is negative, and so the current is also in a different direction. So this is, you can say this is forward, this is backward. Okay, this is forward and that is backward, and this cycle keeps repeating itself. This keeps repeating itself. So you will have this, so forward and backward. So when it is below zero is negative, right? Below zero is negative. So this means current in the reverse direction. This is current in the forward direction. Did you understand? Hala, did you understand?
Yes, miss, I did.
Okay.
Sorry, miss, I confused it with the motors.
No. Okay. Let's move on. Okay, let's do the questions. Simple generator is shown as in figure 43.11. What are A and B called and what is their purpose? Okay, now you guys tell me. So A is slip ring, this circular thing, circular structure is a slip ring. And then this slip ring is then connected to these, an external circuit. These are brushes, okay? So brushes connect the slip ring with the outer circuit. So whatever current this generator is producing is supplied to the circuit via the slip ring as well as the brushes. Okay, so one job is that they connect the generator with the external circuit. Second is that also they make sure that the spinning can continue indefinitely, okay, without any twists or anything. So they prevent the twisting as well. Okay, that they have not mentioned here, by the way, that I understood from the other book, but okay. What changes can be made to increase the potential difference generated? Now you will answer this question. What changes can be made to increase the potential difference generated? I explained you just right now. Myra?
The speed at which the coil rotates can be increased.
Very good. Very good. Good job. And Ajwa, can you tell me another way? Josefa, Laiba?
Use a stronger magnet.
Very good. Very good. Yes. And
Increase the number of coils.
yes. Yes. So increase the number of coils, use a stronger magnet, and increase the speed of coil rotation. Yes, all these three ways, according to these three factors, will increase the potential difference which is generated. Okay, now next. Describe the deflections observed on the sensitive center zero galvanometer here. By the way, galvanometer is a device which detects even small currents. So it's a very sensitive type of ammeter, you can say ammeter, and then we have galvanometer. When the copper rod XY is connected to its terminals and is made to vibrate up and down, as shown by the arrows, between the poles of U-shaped magnet at right angles to the magnetic field, explain what is happening. So just briefly summarize, just tell me what is happening when it is cutting the magnetic field line. Up or down? Yes. Josefa, Laiba, Farrukh. Muhammad, Zainab, Zainab.
Yes, miss.
Yes, beta. Tell me, can you, I'll help you, don't worry. Tell me. So what happens when this conductor moves up? First of all, tell me, tell me where are the magnetic field lines?
It's from north and south, like
Right,
it's
from north to
perpendicular
south.
to the thing.
Yes, perpendicular to the conductor. Okay, now if it is moving up, then what will happen?
And it will cut the magnetic field lines.
Perpendicularly, right? And
Yes.
so then, so that would result in,
Miss, your voice is breaking. Can you please repeat?
I'm saying then, okay, if it is cutting the magnetic field line perpendicularly, and then so that will result in,
It will result in an induced current in the wire.
very good, yes. Okay, now what will happen when it moves down?
It will again cut the magnetic field lines,
Very good.
and then the current will be induced in the wire.
Okay, so any difference between up and down?
No.
No difference. Who will tell me what is the difference between up and down? When the rod is moved up and when the rod is moved down, what is the difference? Yes, who raised hand? Let me see. Okay, Myra.
The direction of the current will reverse.
Right, right. So yes, the direction of the current when the rod is moving down will be opposite to the direction of the current when the rod moved up, right? So the direction of the current will be opposite. Okay, Zainab, keep that in mind. If you don't write that, if you don't write that, you will lose marks. Okay, that is an important point. You cannot miss it. Okay, let's move on to the next chapter. Let's try to do this quick. Okay, transformers. Okay. Okay, the word transformer means what? Transformed into this, from this to this. What does it mean? That has been transformed into this. The ground has been transformed into a classroom, maybe. Changed, right? Transform means change. So we are trying to change something here, okay? So if we have a small voltage and we want, bigger voltage, we can use a step up transformer, like we are trying to amplify, or we are trying to increase the voltage. And maybe we want to, or sometimes in other cases, we might want lower voltages. So then we'll try to diminish, or we'll try to use a step down transformer. So step up transformer increases the voltage, step down transformer decreases the voltage. Okay, and we'll see how that happens. First of all, mutual induction. So again, induction is to pass on the magnetism or a charge or electricity into another object without actually touching it. Okay, that's induction. And mutual induction, meaning both are getting induced. Both magnets or coils or whatever we are using, or both electromagnets that we are using, are getting induced. Okay. Okay, so we are using two coils. They don't have good diagrams. There's a good diagram here. Okay, this one, let's use this one. Okay, this is coil A and this is coil B. Okay, now if we Okay, so we are passing current from this battery, 6-volt DC, into this coil. So we are passing current into this coil, which is turning this into a magnet. Now it's behaving as a magnet. It has magnetic field around it. And now this other coil is right next to it. And so its turns are cutting the magnetic field. The turns of this coil B are cutting the magnetic field. And when that happens, this coil also gets current. So though we did not attach this coil with any battery, but because it was placed right next to this coil, therefore, it also developed a current, right? So this is how the transformers work. But now, if, for example, I increase the number of turns in this coil, so this coil might have more turns than this coil A. Coil B might have more turns than coil A. Then this will, because the turns are greater, therefore the voltage produced in this wire or in this coil would be greater because more lines are cutting the magnetic fields, right? So that's how a step up transformer works. There are more turns in the secondary coil, okay, compared to the first coil or the primary coil. Okay, that's called a step up transformer. Step down, the secondary will have less turns than the primary one. And so smaller potential difference, smaller voltage be induced in it. That's called a step down transformer. Okay. So they are using this rheostat is another word for variable resistor. What do we understand by variable resistor?
A resistor whose resistance can vary.
Yeah, okay. So a resistor, the resistance of which is variable, we can increase or decrease the resistance. So by increasing the resistance, we are decreasing the current flowing through it. And by decreasing the resistance, we are increasing the current flowing through it. So we can control the amount of current flowing through this coil A by adjusting this rheostat or variable resistor. And then this other is galvanometer, which will detect how much potential difference, how much current is flowing through this other, the secondary coil or coil B, okay? So this is how transformers work, okay? Okay. Okay, let me see, okay. Now, instead of moving, just like, you know, we were moving the magnet close and we were moving the magnet in and out, right? And so that was creating a relative motion between the magnetic field lines and the coils. And so therefore, and a potential difference was being induced. Instead of doing that, what have they done? They have used AC. Okay, they have used AC. So the primary coil is attached to AC. Now, what will AC do? That it will pass the current in one direction, which will be like magnet coming closer. So current being induced in one direction. And when the current is flowing in the reverse direction, that will be like magnet being pulled out. Okay, correlated with this magnet being moved in and out here. So here the direction of current was one, and here the direction of current was reversed. Remember? So instead of bringing in and moving out, because you cannot keep doing this, right? Instead, what they did is that they connected the primary coil, because primary coil also behaves as a magnet, right? When current flows through it. So they connected it with AC. Now it is behaving as a magnet which is coming in and going out, coming in and going out, coming in and going out. So there is constant relative motion of magnetic fields with the turns of the secondary coil. And that will induce current and potential difference in this secondary coil. That can be used to for any purpose, for lighting up a lamp or anything. Okay. Now, in order to increase the strength so that they can have a greater voltage produced, what they did is that they used a soft iron core. They wrapped these wires around a magnet. Now, what this magnet does is that it makes the magnetic field lines stronger. Because if you don't use this soft iron, even then these two coils will behave. I mean, they will behave the same way. There will be voltage produced, but the voltage will not be that great. You won't have bigger values for voltage. If you want higher voltage, like for factories or industries or for a particular area, you need high voltage, then what they have done is that they have tried to increase the concentration of magnetic field lines. And how have they done that? By using this soft iron core. They call it core because it's passing through the center of this whole structure, this whole thing. Okay, so they have used a soft iron core, and they have also attached the primary coil with AC. Okay. Okay. Find the effect on the brightness of the lamp of pulling the C cores apart slightly. Pulling the C cores apart slightly. What do you think will be the effect on the brightness of the lamp if the C cores? Do you think the magnetic field lines would move or they would get weaker? Yes, Hala?
They'll get weaker as they're apart, and they'll cut off less. The wire will cut off less magnetic field lines.
Yeah, I think so too. Yes, you're right. Okay, the effect of increasing the secondary turns to 15. Increasing the secondary turns. Increasing. We are increasing the turns. Secondary turns to 15. Increase in the voltage, and therefore the lamp will light brighter. Decreasing the secondary turns to 5.
Decreasing the voltage.
Yeah, it will become dimmer. It will become less bright. Okay. Okay, let's move on to the equation. Transformer transforms or changes an alternating voltage from one value to another of greater or smaller value. So if you are using a step up transformer, you are changing to a greater value. And if you're using a step down transformer, you are decreasing the value of the voltage. And so, yes, okay. Now, the voltage which is produced in the secondary coil is directly proportional to the number of turns. Okay. And I mean, in any coil, in any metallic wire which is coiled up, the voltage which is produced is directly related, is directly proportional to the number of turns. Therefore, the ratio of the voltages will be the same as the ratio of the number of turns in the primary and the secondary coils. Okay, the ratio of the voltages, just remember this. If you cannot remember the equations, just remember this, that the ratio of the voltage will be the same as the ratio of the turns. So then you solve these questions just as you solve ratio questions. The ratio questions in math, this is done the same way. Okay, what is this? This is ratio of voltage, and this is the ratio of turns. That's all. Okay, these are the symbols that we use for step up. This is a step up, so you can see that the secondary coil has greater number of turns, greater turns compared to the primary. And this is a step down. The secondary one has less turns as compared to the primary ones. The primary coil has greater. Okay. Okay, another thing is that, remember, principle of conservation of energy is applicable here as well. Though we are increasing and decreasing the voltage, but the total energy will stay the same. the energy between primary and secondary will stay the same. I mean, almost the same. There, of course, there are energy losses. Okay, there are energy losses. Nothing is ideal, right? In this real world, nothing is 100%. So there are losses of heat to the environment, but neglecting those, we can say that the energy transfer is 100%, neglecting those. Okay, but we will have to discuss where the energy is lost. We will discuss that later, but first let me discuss this power thing. So you understand power, right? Can anybody real quick recap what is power? What is power? Yes, I'm waiting. Power. नहीं आ रहा किसी को भी? यार फिर मैं नहीं पढ़ाऊंगी, ठीक है ना? अगर आप लोग ऐसे करेंगे ना, फिर मैं नहीं पढ़ाऊंगी.
Yes, I don't know.
This is it energy transfer over time taken?
Very good. Yes, thank you, Shamim. Yes, very good. Yes. Power is energy transfer divided by time. So the rate of energy transfer. Okay, E for energy over time. Okay, T for time. So yes. And in electric circuits, power has different formulae. I don't know if you remember, but if you don't remember, then learn it. Okay, power is VI, and then this is in other chapters in the power chapter. Okay, you can real quick go, I mean later on you can go and have a quick skim through those pages. When you look at those pages, it will come back to you. Okay, VI, power is equal to VI, and for a resistor, it is I square R. And I think there's another equation, but I'm not discussing that other equation. There's a third one. The third one was V square over R, if I'm not mistaken. Yeah, something like that. But we will use these two for now. So since energy is conserved according to the principle of conservation of energy, so we will assume, remember, this is just an assumption. In practical life, energy is lost. It's not the same between the primary and the secondary coils. Some energy is lost. So we will assume that power in primary is equal to power in secondary because the time spent is the same. Yeah, okay, forget the time. So because the energy is the same and time is the same, therefore power is the same. Okay, this is what I was trying to say. So if the energy, we are assuming that the energy given by primary and taken by secondary is the same, and time for both of them is the same, therefore power is also going to be the same. And power equation is VI. Power equation is VI. So from this equation, considering power in primary is equal to power in secondary, the product of the primary voltage and the current in primary coil is going to be equal to the secondary voltage and secondary current, meaning current in secondary coil. P for primary, S for secondary. Okay. Please turn off your cameras. Okay. So now we rearrange this equation. When we rearrange this equation, we come up with this, but this is easier to remember. Okay. You can always rearrange and come to this equation. Just remember this one. VP IP is equal to VS IS. Okay. Now, let's talk about where the energy is lost. I was saying that energy is lost to the surroundings. Where is it lost? Any ideas? Common sense? Any ideas?
In the resistor?
Yeah, sorry?
Is it lost in the when it's facing a resistor?
Yes, you are correct. Yes, wonderful, Shamim. Yes. So resistance of wires. So when the current is passing through the wire, of course, although, I mean, no, there is no conductor which has zero resistance. Every conductor has some resistance. Some have low, some have high, but they will have some resistance, okay? So that resistance will result in conversion of the electrical energy loss as heat, thermal energy, just like friction, energy is converted into heat, which is wasted, energy which is wasted and we cannot use it. Similarly, in electric circuits, resistance is that friction. Okay, think of resistance as friction of electricity. Yes, so that is one loss. Then this iron core that we use to strengthen the magnetic field itself is a metal, right? Iron is a metal, and so it will also conduct electricity. When it will conduct electricity, it also has some resistance, and it will have these currents because it is also conducting. So when the coils are behaving as magnets and there is a conductor close to it, some currents are induced in the iron as well. Do you understand me? So these wires themselves are magnets, remember? Even without the soft iron core, they were magnets. But we try to strengthen, we try to increase the number of magnetic field lines, because more the magnetic field lines are there, stronger the potential difference we will get. So we were trying to do that, right? But also remember that this is a conductor itself, and it is close to these two magnets. And so some current is induced in this iron as well. Okay, that current is just lost. It's not useful for us. And these are called eddy currents. And it just goes to waste, and it just warms this up. It just is lost in the form of heat, thermal energy. Okay, these are called eddy currents. This is the second wastage. One was due to the resistance in the wire. Second, eddy currents in the soft iron. So how do we overcome this problem? How do we overcome the problem of eddy currents? What they do is that they try to increase the resistance of this iron core so much that it becomes an insulator. How do they do that? Is that they cut this, or somehow cut this iron into thin layers, thin layers. Like if you have this, for example, this is the core, this is the iron, right? Now what they'll do is that they will cut this into thin layers, and in between the layers will be insulated material, insulators. In between, there will be insulated material. Now, what have they done? To understand this, you have to know what factors increase and decrease resistance. Do you remember the factors which increase or decrease the resistance? Remember, the less the diameter, the greater the resistance. Do you remember that? Okay, so now each layer is behaving as one wire. So the resistance of each is greater. And if you add them up, the resistance will be quite high. So they will behave as many layers together. And so overall, this will increase the resistance and will not allow eddy currents to flow through them. They will resist eddy currents. And therefore, the energy will not be lost in the form of heat. That's what they do. I hope you understood. And also in between the layers is an insulated material. So it does not allow the current to be transmitted from one layer to another. And also each layer is like very thin. And so less the diameter, greater the resistance. I hope you remember that. And I hope you knew that already. And then third factor that they have discussed, which leads to loss of energy, is the leakage of field lines. Not all the lines are cut by the secondary coil. Okay, some of the field lines, because the secondary coil is not as big. So some of the lines are lost. They are just lost uncut. They just go uncut. Okay, so if the electromagnet is badly designed, so An efficient electromagnet should be designed in such a way that it should ensure that all the magnetic field lines are being cut. Okay, now this is a worked example. Okay, you want me to do this with you, or is this easy? How many want me to do? You can raise your hands. This worked example. Or should we move on to the end of chapter questions?
Miss, can
Yes,
you
we can
please
move
do
on.
the example?
You want? You want it?
Yes, Miss.
Okay. Okay. As transformer steps down the main supply. What does this mean? A transformer steps down the main supply. So that means the voltage is being decreased from a high value to a lower value, okay, to operate an answering machine. Okay, one thing I just remembered, I forgot. This thing reminded me. When I said that the power, remember this equation, that the power in the primary is equal to the power in the secondary coil, assuming that no energy is being lost in this, appreciate a fact that when the voltage decreases, the current increases. Why? Because they have to stay equal, right? They have to stay equal. So in order to be equal, if the voltage goes down, the current has to increase. Otherwise, this will be a lower power. This will be lower than this. They cannot be equal then. Okay, so don't be confused. Remember, step up and a step down are for voltage, not for current. So just think in terms of voltage, and then the opposite will be the current. Okay, this way you won't get confused. So step down, meaning voltage decreases, but what happens to the current? Increases, okay? Because the power has to stay the same. If both will increase, you will have a smaller value. If both will increase, you will have a greater value, but they have to stay equal, okay? I hope you understand that. Okay, so here the voltage value is decreasing from 230 to 10 volts. So that this is a step down transformer to operate an answering machine. What is the turns ratio of the transformer windings? Ratio. Now the ratio of the turns will be the same as the ratio of the voltage. Okay, and remember, by convention, we write secondary at the top and the primary at the as the denominator at the bottom. But it's not. But even if you write the other way around, you will get the same answer. The answer will be the same, but conventionally we write secondary at the top and primary at the bottom. Okay, so secondary is 10. Secondary is what you are getting. That is secondary. Okay, what you are as output. Okay, what output are you getting? So secondary voltage is 10 volts, not 230. It's 10 volts. Okay, 10 will come at the top, and then primary was 230. What is your input? Input was 230. Okay, 230. And so 0, 0 get canceled. So they are asking the ratio. Ratio meaning they are asking this. They're asking this. So the ratio is 1 over 23. That's the ratio, 1 over 23. Okay, same working. Okay, how many turns are on the primary if the secondary has 100 turns? So using this ratio, what are they asking? How many turns are on the primary? So they are asking me primary. So let me write it this way. Primary, they're asking primary, right? And secondary, they gave me 100. Okay, so now cross multiply. So number of turns in the primary is 2300 turns. Okay. Did you understand how I did this? So I used this ratio. This, remember, this was secondary, this was primary. So I will write secondary at the top, primary at the bottom. And so the number of turns in the primary coil is 2300. Okay, is there any question? Did you understand? Is this clear? Okay, now part C is asking what is the current in the primary if the transformer is 100% efficient and the current in the answering machine is 2 amperes. So why have they mentioned 100% efficient? Because they want us to neglect any heat losses. So there are heat losses, as we just discussed, due to resistance of wire, eddy currents, and due to the leakage of field lines. But neglecting all of those, because the energy is the same, so power will be the same. So we will use this equation. Power in primary is equal to power in secondary. Okay, because energy transformed is the same. So again, okay, let me just follow them. VPIP is equal to VSIS. Okay, and then plug in the values. Okay, VP was, primary was 10, here 10. And they are saying that the current in the answering machine is 2 amperes. That means the secondary current output. Secondary output is 2 amperes. Okay. Or maybe I should solve this myself. VPIP is equal to VSIS. Okay. This was my VS, 10 volts. Can you see my working? Okay, 10 volts. And they're saying that 2 amperes is the IS, and they're asking me IP, and primary voltage is 230. Okay, so now it's easy. IP is going to be 10 multiplied by 2A divided by 230. Okay, that is going to be 0.09 amperes. Okay. Okay. Is there any question so far?
No, Miss.
Okay. So now they're telling you the uses of these transformers in national grid system. You know, they use these step up and step down transformers. So when you have high electricity coming from the main supply and you want to supply electricity to small houses, you use a step down transformer. If you're supplying to a big heavy industries, then you will use a step up transformer, and so on and so forth. This is what they're saying. Okay. Yes, there was one interesting point here that they mentioned, is that in these cable supplies, in these cables which are bringing electricities to houses and industries, what they do is they use high voltage and low current. High voltage and low current. Why? Because if see, power was VI, right? VPIP is equal to VSIS, right? So when voltage is high, I told you the current is low. Okay. For a resistor, it is this I squared R. Remember? So it's going to be I squared R for a resistance. The power is I squared R for a resistor. Now, can you see for a resistor, for the power of a resistor, current is very important. Current is very important. If you have high current passing through cables, now cables also have resistance and the current is high, and you know cables are extremely lengthy. Also, you should remember that longer Longer the length of a wire, greater the resistance. Remember, longer a wire, greater the resistance. So cables are really long because they are bringing electricity, I don't know from where, from the main power supply that might be miles away from your house or from the industry that they're supplying. So the length is a lot. So resistance is high. Resistance, this is high. So what they try to do is decrease the current. Because this is high, they want to decrease the current because they don't want the energy to be lost in the form of heat. Okay, so when the energy, when the current is low, if they are lowering the current, they will have to increase the potential difference. Okay, that is why, that's the point they're trying to make here, is that other than insulating the cables properly, other thing that they use to minimize heat loss, minimize energy loss, is that they use high voltage across the cable and less current. Less energy will be transferred to heat if the power is transmitted at the lower current and higher voltage. Okay, the power lost as heat in cables of resistance R is I square R. So I should be kept low, and you can see that I is getting squared. So if you're using a big value for I, it is getting squared. I mean, a lot of power will be lost. A lot of energy will be lost. Okay. Now let's move on to the questions. Is there any question so far?
No, miss.
Okay, 2 coils of wire. You guys don't ask any questions. Is that because, anyway, but I don't like it, okay? I want you guys to be asking questions so that I know that you are with me. Or is it that people scold you when you ask questions and so you guys have decided on not ask? Better not to ask. Okay, 2 coils of wire A and B are placed near one another. Coil A is connected to a switch and battery. Coil B is connected to a center reading moving coil galvanometer G. See, when people don't ask questions, there are 2 possibilities only. One is either you are very, very smart, you're understanding 100%, and you have no questions at all. Second is that you are not paying attention enough to ask questions. So it can be either of the 2. 2 coils of wire A and B are placed near one another. Coil A is connected to a switch and battery. Coil B is connected to a center reading moving coil galvanometer G. If the switch connected to coil A were closed for a few seconds and then opened. So they are talking about this picture here, 44.9. We have 2 coils. One has a switch connected to a DC battery, and the other is just a simple coil. It has no battery, but it has a galvanometer. Now, if it is open and then closed, what change will you observe in B? I think that's the question. So tell me, if the switch connected to coil A were closed for a few seconds and then opened, the galvanometer connected to coil B would be affected. Explain and describe step by step what would actually happen. So keeping the explanation in mind that we just discussed. Very good, Hala. I appreciate your participation and your courage. Yes, go ahead. Yes, Hala.
As the switch is closed, the current passes through coil A, and this causes a magnetic field around the wire. As the coils are placed together near each other, there will be mutual induction, and
Very
there will be a
good.
transfer of voltage to coil B, and
Okay.
thus there will be deflection of the needle of the galvanometer.
Very good job. Yes. So, but just one thing that do mention that the as we close this switch, the current will flow, yes, you mentioned, and then magnetic field lines will develop. And as they will develop, they will be cutting the turns of coil B. So it's equivalent to bringing a bar magnet close, right? It will be equivalent to bringing a bar magnet and, you know, moving it inside. And so that will induce a potential difference of voltage and therefore a current in coil B, which will move the needle of the galvanometer. Yes. Okay. Then part B. What changes would you expect if a bundle of soft iron wires was placed through the center of the coils? Give a reason for your answer. What would you expect if a bundle of soft iron wires was placed through the center of the coils? Give a reason for your answer. Sundar? Beta, aa jaun. Okay. Yes. Ajwa, come on, you tell me. I want somebody else as well. Muhammad?
Increase the reading on the galvanometer.
Yes, very good. So you know the answer, then why don't you volunteer? Why don't you come forward? You know it. Yes, very good. Yes. Yeah, so, but explain it a little. Say that when we use soft iron core, the strength of the magnetic field will increase, so more field lines will be cut by the turns of coil B, and so greater potential difference, therefore greater current. Okay, C. What would happen if more turns of wire were wound on coil B? अब ये तो easy है ना? Ajwa, Huzefa, Naba, Shambleed. Come on. Sundar, you tell me. You're increasing the number of coils, no number of turns. Louder.
So you increase the voltage.
Yes, so increase the voltage and hence increase the galvanometer reading, right? Question number 2. The main function of a step-down transformer is to decrease the current, decrease the voltage, change AC to DC, or change DC to AC, decrease the resistance of a circuit. Sundar?
B,
जोर से बोल दो यार.
Decrease the voltage.
Yes, 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 Ajwa, correct. Decrease the voltage. Calculate the number of turns on the secondary of a step-down transformer, which would enable a 12-volt lamp to be used with a 230-volt AC mains power if there are 460 turns on the primary. So first tell me, by looking at the question, what formula will we use? We have come across two formula in this chapter. One is Vs over Vp is equal to Ns over Np. The other equation was, the other formula was Vp Ip is equal to Vs Is. So which one?
Vs
So
over Vp.
The first equation.
Yes, Vs over Vp is equal to Ns over Np. Why? Because they have given us the Vp and Vs and the turns. So Np, they have given us Np and they're asking us Ns. Okay, so this is easy, right? Just put in the values and you will get it. Is equal to Ns over Np. Tell me, what was Ns or what was Vs?
12 volts.
Very good. 12 volts. Why? Because 12 volts was the output, right? Vp was, Vp is
230 volts.
230. 230. And Ns we have to find out. Np is
460.
460, right? So you know this, right? 460. 460. So 212 are 24 volts. Sorry, 24 turns. Yeah, be careful of the units. Okay, 24 turns, right? Okay, let's move on. What current will flow in the secondary when the primary current is 0.1 amperes? Assume there are no energy losses. So which equation? Which formula?
VPIS, VPIP is equals to
Yes,
VSIS.
yes. VPIP is equal to VSIS. And so VP is, again, this was
230.
VP is 230. VP is 230. IP, when the primary current is so IP is 0.1. VS is 12, and IS we have to find out. Okay, so 23 divided by 12 is equal to IS. What is it? Use a calculator. I don't have. Okay, so whatever the answer is, that much current. Okay, question number 4. A transformer has 1000 turns on the primary coil. The voltage applied to the primary coil is 230 volt AC. How many turns are on the secondary coil if the output voltage is 46 volt AC? Which formula? So whenever you see turns, whenever you see the word turn, you know it is Vs over Vp is equal to Ns over Np. That formula, right? Sorry, Vs over Vp is equal to Ns over Np. Has 1000 turns on the primary coil. So Np is 1000. Ns पूछा है ना? हाँ, okay. Ns. Vs. What is Vs? 46. And Vp is 230.
230.
Right. Okay. So 46 over 230 multiplied by 1000 equal to Ns. 0, 0 cancel. 200 turns. 200 turns in the secondary coil. Okay, 200. So therefore option B is the correct answer. Okay, so we are done. Alhamdulillah, 2 chapters done. Any question? Any question at all? Okay, then
No, miss.
tomorrow. Okay, then tomorrow we will try to finish 45, chapter 45 and 46. 45 is electromagnets and 46 is electric motors. Okay, inshallah, inshallah. Okay, so this will help me. Okay, so then see you tomorrow. If there's any question, please let me know. Okay, assalamu alaikum wa rahmatullahi wa barakatuh.
Allah Hafiz, miss.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz.